Hello everyone to today's webinar about rapid reaction monitoring of stop flow application. My name is Florian Eigenmann from IRis-F1 and I'm your host today. The webinar will be given by me and Raphael Horvath, Senior Application Engineer at IRis-F1, who conducted the measurement and will last roughly 30 minutes. Okay, here's the outline for today's webinar. We talk, or me specifically, I will talk first about applications with Dual-Comb Spectroscopy, which we recently did. Then also the previous work on fast curing processes of adhesives. Then I will take over, or I will hand over to Raphael, who will go into deep about stop flow applications. This is an outline, and here you have an overview about all the applications which we dealing with at the current status. Specifically, we did a lot in protein kinetics, combustion diagnostics, and of course also now flow chemistry. And I will also give you an overview about some applications we have done in photochemistry, heterogeneous catalysis, electrochromism, polymer chemistry, and trace gas analysis. So those are the benefits which you achieve with the IRis-F1, especially with the Dual-Comb Spectroscopy. And for today's webinar, we focus on speed, on fast processes with high throughput. Our slogan from IRis-F1, it's all about time. This is very important. We have actually monitored and presented already like 25 spectra per second is possible with this kind of technology. Raphael will dive a little bit more into it. We showed already at several conferences as well that it's already possible to go down to 100 spectra per second, 100 hertz, so with increments of really 10 milliseconds. This is the results we recently presented, reaction monitoring in real time and in situ. This is a reaction which we have done with the company Delo, and they kindly provided us their adhesive, a reaction actually which lasts 3 to 5 seconds, hardens in 3 to 5 seconds, and it's impossible with standard FTIR spectroscopy to monitor the kinetics there. Now I hand over to Raphael Horvath. Raphael actually, he received his Ph.D. in chemistry, in specifically Raman spectroscopy at the University of Otago, New Zealand. He worked on resonance Raman spectroscopy there. Then later he worked 5 years as a research fellow in ultra-fast infrared spectroscopy at the School of Chemistry at the University of Nottingham. Since 2 years, Raphael joined IRis-F1, and he's our Senior Application Engineer. Please, Raphael, go ahead.
Well, thank you for the nice introduction, and also thanks everybody for coming. Today, as Florian mentioned, I will mostly talk about stopped flow and the experiments we did around stopped flow. And to really benefit, I think it's worthwhile to go a little bit over the principles of Dual-Comb Spectroscopy. I won't go very much in depth. If you are more interested, there's a website here, irsweep.com/technology. You can learn more there, or alternatively, contact myself or Florian. Will be happy to answer any questions either during this webinar or at any time later. But some things do need to be sort of addressed here. The first thing is in a dual-comb spectrometer, as the name suggests, we use two frequency combs, so two lasers, and they are based, in our case, on quantum cascade lasers, so that makes it a turnkey instrument. So you literally turn it on and it works in most cases. A spectrum of a frequency comb is shown in the bottom right. This is sort of a typical device. They tend to have coverages of about 60 wave numbers in our cases. And really the crux of this technique is that you can use, you can define the electronics of these chips in such a way that you can use a heterodyne detection scheme. In other words, you use radio frequency detection, and it takes away all the moving parts for a spectrometer. It's just two lasers going through a sample, hitting a detector, and you can measure as fast as you want to a certain limit that is given by the lasers. But it's a solid state technique. So the main things I want to sort of get at with this slide is that we have high power because we have lasers. High resolution is a very useful property to many people. We won't talk so much about high resolution here today. For a laser, it's quite a broad spectrum, and it's fast in part because there are no moving parts, but it's a little bit more subtle than that, and I'll get into that later. So if you've ever seen any of our presentations, we normally talk about timescales of microseconds. So this spectrometer really shines at short timescales. And we can do sort of late nanoseconds to milliseconds in a single acquisition quite well. This particular talk really extends that from the milliseconds to the minute timescale, in part because many chemists are actually more familiar with those timescales, and it's more useful for them to work on those timescales. So we want to push it in this direction. And that's where stopped flow is a very useful application, because it actually is meant to be for fast reactions. So these are the two different timescales that we're moving through. So this talk is mostly about milliseconds to minutes. Here is a spectrum, so a heterodyne spectrum of a typical comb. This particular one is in the 6 micron region, or 1650 inverse centimeters. And you can see there are these holes in the spectrum. And if you plot the standard deviation of signal per spectral element here, which is shown at the bottom, you can see there are essentially what looks like a water spectrum. I mean, these are bands, and if you've ever worked in this region with infrared spectroscopy, you will recognize that there is a lot of water in this spectral region. And in fact, you can fit this to water vapor out of hydran. And what we're really seeing is water absorption here in an unpurged spectrometer. These obviously go away if the spectrometer is purged. So that's the typical coverage that we work with. And the transmission standard deviation in the bottom part of the figure also tells you about the typical noise levels that we achieve. So less than 0.01 OD in a sort of 100 microsecond integration time. So it's quite a low noise technique for the time scales that we're working with. So this is a setup, so it's a kind of an exploded view of the spectrometer. The main thing that the user interacts with here is the sample compartment. You can see in blue is the beam that goes through it. It has been, in our case, in all the experiments I will show you, actually, we use an ATR accessory for ease of detection, well, ease of setting up. And the detectors are thermoelectrically cooled MCT detectors. So I will just quickly touch on the acquisition scheme, because normally when we measure on the microsecond or even faster timescales, we use a slightly different acquisition scheme. But in this case, if you've ever used FTIR before, this will be very familiar to you. So you do a background measurement, and then you do a series of sample measurements. And here the acquisition frequency, so in other words, the gap between the sample measurements, is really what defines your time resolution. And because we do an all-electronic detection scheme, to an extent you can make this as fast as you want until your computer can't handle it anymore. So onto stopped flow. A very kind of primitive picture of stopped flow is shown here. You have two reagents that are injected into a mixer where they will start a reaction. This is then stopped, and then you can measure. And you can use a variety of techniques to measure. This talk being about infrared, I will tell you that infrared is one of the better techniques for this. It gives you structural information, and it can also give you time information. So it really does a lot of things for stopped flow. A real setup from a leading manufacturer is shown here. You can see on the left there's quite a heavy-duty pump setup where the solutions are mixed essentially. The center part is the spectroscopy unit, and on the right is controlling electronics. So this can be very well controlled, and you can inject and therefore measure on a time scale of milliseconds. So it is mechanically a very robust and well-established technique. However, in our case, what we did, we used syringes because this was sort of a first proof of principle. We wanted to see how fast can we measure, does it really work, is it useful? And the best thing to do at this stage was to just use these syringes. That means the kinetics will be not as accurate, but otherwise you should see comparable results. So we use a commercial ATR prism with a stop flow accessory, and this handheld syringe feed. Unfortunately, I can't tell you exactly what the reactions are that we're looking at because it's still under NDA. Hopefully this will be released in the not so near future, or not so far future. But essentially we have a two-step reaction, reagent A, reagent B, that makes one product. And this product C then goes on to react to product E through a further reagent. So we're looking at both reaction steps. Just a bit of background on how we got into this. As Florian mentioned, Delo, a German company who makes adhesives, wanted us to look at one of their curing processes. And this is very useful because it uses UV light. It's very easily triggered, and it's quite fast. And here we say we can measure with 40 millisecond increments, so 25 hertz. The title of this talk, I think, measures 50 or mentions 50 or 100 hertz. There's a bit of inconsistency in this. It's partially because we're going quite fast into software development, and a lot of this is limited by software and also by the computing hardware. So it's quite easy to upgrade existing spectrometers to go much faster. So here we do 25 hertz. Then we moved on to doing curing of dental glues. This was in collaboration with the University of Zurich. Here we measured at 100 hertz. So we're already 4 times faster, and we think we can make it still faster. On the right-hand side, you can see the kinetics at multiple points of these different glues that we measured, and you can see actually that there's some curing happening before the light turns on, and then also obviously faster after the light turns on. So back to stop flow. This is the first reaction step, and if you are a chemist who uses FTIR quite a lot, you can probably recognize that this is a double bond of some sort. So you have the disappearance of A and the appearance of C. The double bond is shifted to lower energy somewhat. And if you want to, you can look at 1670 and 1650 to really follow these reactions. What you can see is where it says syringe movement on the right, the operator really was moving their hands a little bit, and you see some fluctuations, but then they held still enough after about 1.5 seconds. And you can see sort of this is a bi-exponential decay. I mean, we can't fit it exactly because it's still this the syringe-driven setup, but it's bi-exponential, so it's probably a first-order reaction, and that's already quite valuable information. And in this case, we're getting 50 spectra per second, and this has been averaged to 2.7 reciprocal centimeter spectral resolution. So I'll get a bit into noise comparison because a lot of FTIRs have a rapid scan mode, and they can measure down to on the order of about 20 milliseconds as well. However, where they really kind of fall behind is when you look at the signal to noise. It's mostly due to the light source, and we have lasers. We do quite well in photon limited applications like this one. If you have a thermal light source, it's quite difficult to get the same signal level. So it's really the brightness that enables the speed. It's not just the fact that we don't have moving parts. You also need to be able to provide the light. This is the product formation step. So this is the second part of the reaction. So here we have product C from the previous reaction is now being consumed. And here we're measuring at 100 spectra per second, and there's a final product being formed, product E, which is the actual desired product. Again, there's some syringe movement at the start, and then there's a steady state reaction part. Fitting suggests that this is a slower reaction than the first one, but again, to put exact numbers on, I think would require some sort of mechanical pumping to really nail down the kinetics of this. I will go a little bit more into the processing of things. So on the left, so this is how I did the data treatment of these. So on the left, top left, you can see the raw spectra essentially. They come at 0.3 reciprocal centimeter resolution, so they're quite high resolution. And most people don't need that, and they would say, no, that's not for me. However, you can also see water lines in there, and this is again we're working in a water-rich region of the atmosphere, so there's this atmospheric interference, and because the lines are so narrow, you can actually reject the water lines very easily. So so what we've done in the processing is we use the standard deviation of the signal, which is given in this plot at the bottom, and automatically filters out for regions of higher standard deviation than the surrounding regions, and that gets rid of the water lines. And then we did some spectral averaging from 0.3 to 3 approximately reciprocal centimeters. So there was no real magic behind this. It's just taking out. This is basically what you can automate this because you have all the information of the standard deviation, and it really cleans up the spectra. I will show you a more extreme example of this. So this is now on the microsecond time scale. So each individual line is a 5 microsecond integration time. And here the spectroscopist forgot to purge the instrument. So on the left you can see it's just a mess. It's dominated by water lines, dominated by regions of extremely high standard deviation. Now, after doing some water rejection and some spectral averaging, I think in this case to about 5 reciprocal centimeters, you get a very usable spectrum. And this is just a filtering process. There's no fitting. There's nothing being invented here. It's just taking out the lines that we know are bad from the standard deviation. So where to next? We're only just sort of getting started with stopped flow. We're hoping to do many more experiments. A lot of the stuff we're doing next is really driven by the applications and the customers and what they want to do, and faster is one of the things. So we want to really reach the limit of what the stopped flow equipment can do. We don't want the spectrometer be the limiting factor. So at the moment we can do 150 spectra per second in the current software. We can already do 250 spectra in the lab under some conditions. And I should stress that this is with equal integration times. So you're not trading time resolution for signal to noise. You're actually gaining in signal to noise as well. It's just a matter of optimizing the processing, adding more memory to your computer and things like this. The hardware limit ultimately is at 1 microsecond per spectrum. Whether we can combine this with the minute time scale is to be seen. But if somebody really wants it, we can certainly try. Flexible triggering schemes would also be interesting. So if you look at the plot on the right, you recognize most reactions undergo this kind of process, and unless it's a zero-order reaction, it will be much faster at the start than it will be at the end. So if we can change the triggering throughout the reaction, that will really expand the dynamic range of the measurement in terms of timescales you can probe, and put more emphasis in terms of signal to noise on earlier times or whatever times you want actually. So having a dynamic sort of triggering scheme is something that we're looking to implement. We also want to fiber couple for production environments and also just people who like to work with fibers. There are various advantages. The current limit is at about 2 meters, and having a laser, we think we can increase this significantly as well. And then obviously laser improvements. People want broader lasers and cover more ranges. We want to cover the entire mid-infrared. And I think sort of, all of these things put together, I think are going to make this a much more powerful technique in the future. So I think that's it from me. I will hand back over to Florian.
Thanks, Raphael. This was for this very interesting talks. Actually, we got already some questions over the chat. It's actually also important to announce that you can address all your questions in the chat box and send it to us as we talk. We have still plenty of time, and we will address all the questions. A few questions which already popped up was actually, is it compatible with Precursor ATRs?
So the answer is yes. In terms of the sample compartment, it is modeled after other commercial already existing FTIR, so it's very interchangeable. The beam height is the same. The alignment is usually, in fact, easier because we have a laser rather than a thermal source. But occasionally, you need to put a piece of optic in to make the alignment properties the same. So in a typical FTIR, the sample compartment has a focused beam, and we have a collimated beam. So those are the main differences. But we've never had an accessory that we couldn't put into our instrument and get it to work.
Okay. Then another one you mentioned about the moving parts in this technology, that there are no moving parts specifically in this technology.
That's right.
Unlike other spectroscopy or other spectrometer on the market. Is that actually the reason why you get such nice signal-to-noise ratios?
So it's one of the reasons. I would say that the biggest contributor to signal-to-noise for these measurements is the high light intensity. We're working in photon-hungry applications, so that's where laser really shines in terms of performance over thermal sources.
Okay, thanks. Then there's another one. Can I use different laser wavelengths models? I mean, you showed a little bit the limitation there also compared to FTIR, where you have roughly like 60 to 100 wave numbers. Can you change such modules, and how long do you need for changing such modules?
Yeah, so everything I've shown today was with one module, with the 1650 module. But we have actually a picture here that depicts how you can change these modules. So you can just take one out, put the other one in. The actual physical exchange is done in a few minutes, and then you need to let it stabilize for 30 minutes or something like this before it's really ready to use. But it's quite straightforward to change the modules.
Okay, thanks. Then another question which popped in is here, like, can those water lines be easily, also if you have water lines which you showed, can they be easily removed with just software, or can you purge the spectrometer?
Mm-hmm. So you can use, yeah, there are two ways. You can use the HyTran data that is available. To do this, you first need to do very accurate calibration. A slightly more sort of I would say possibly more robust is just to use the standard deviation that comes out of the instrument, because for lines where the water absorbs the light intensity, you have very high standard deviations. You can see that in the output data, and then you can give those lines a lower weight in an averaging algorithm. So it's already in the data, the things that you need. But you could certainly also use HyTran or another external database or previous measurements to do this rejection.
Okay. Then you mentioned on one of the last slides actually what's next, and you said something about fiber optics coupling. Have you done already some experiments about which underlines actually that you can go to much longer distances? Because you mentioned something about the current limit is around 2 meters. So.
Yes, so we have done some fiber optic coupling for an existing customer who use fiber optics in their work. We haven't measured the length limitations yet. We haven't really pushed it to how far it can go, in part because mid-infrared fibers simply don't exist at those length scales yet. But that's definitely something we want to characterize, and then I think most of the losses come from coupling. Well, a lot of the losses come from coupling in and coupling out, and then changing the length, I think if you have a high enough intensity, should definitely be possible.
Thanks. Okay, at this time we don't have any other questions, but we are still here. I mean, if there are some other questions come up, always send us an email or go on our page on www.irisweep.com. You have also the possibility, as I said, just send us an email on info@irisweep.com. We will be available. Thanks, Raphael, for this excellent webinar and for your attendance. Thanks a lot.
Thank you. Bye-bye.